So today, so I like a lot the idea of simplicity and complexity and how actually complexity actually is good in terms of is essential in terms of not only science but also our life actually. So today I want to talk about galaxies and how galaxy formed. By the way, if galaxy didn't form, we would not be here today giving this, listening here to to my talk in particular, but also to other things. Okay, so let's see. So in cosmology, we study the origin and evolution of the universe. And in particular, in 1992, up to now, actually, many, and even in the future, many studies appeared in terms of studying the ripples in the energy, we're going to see in the next slide, of primordial light, actually. And in particular, we want to ask the questions, how come, how come galaxy formed out of, the initial universe, actually? So galaxies were not there forever, okay? So it was not like our sun was there forever for, and then will be there forever, actually. That was actually what most people thought, in the centuries, actually. Things were unchangeable, actually. But no, we have evolution, actually. Maybe we have a de-aspartame in the universe, which makes it aging, actually. All right, so then we have this, but we had to see why we have galaxies, actually. Because this is what we see, right? It's easy to know what we see, but it's quite difficult to, to understand why. All right, so this is what I said in the ripples of primordial light. You see this image is being taken by 3 different experiments. This experiment here got a Nobel Prize, and you see, let's say, 10 years later, around 10 years later, we got this more improved version of this picture, and now, again, after 10 years, we got a much more improved version of this picture. What is this picture, by the way? This picture is the following. There is some light, but we don't see. It's like microwave light all around the universe. All right? And that's already something which is, the people who first found it got a Nobel Prize. Okay? There was no explanation whatsoever that light was coming from Earth. And that light was exactly all the same all over the place. Okay? Now, this doesn't look like it's the same, but you see there are some red colors and blue colors, but these red and blue colors are actually 1 part out of 10 to 5. So this has been exaggerated. Reality would be something which is completely 1 color only. Would be more homogeneous than this wall. This is looks very homogeneous white. That would be much more. Okay? That's probably the thing that is most homogeneous we know in the universe. But homogeneous means everything is the same. So extremely simple, right? So that's the universe. That was the picture of the universe. As I said, it's whole homogeneous. They removed the homogeneous part, and these are ripples, very tiny ripples. It's like you have a sea, right, which is completely flat up to 1 part up of 10 to negative 5. Essentially, you will not see by eye. It would look like a mirror, perfect mirror, something we never experienced in our life, such a calm sea. Right? So that is something that the universe was like that. So no galaxy, and the universe was extremely simple. Because anytime, anywhere, you will go, okay, it's the same here, the same here, the same there. Temperature here, the same, the same, the same, the same. Right? So then question is, well, hold on a second. All right, so that's a picture of the universe. But so what happened today? So the universe was extremely smooth, everywhere the same. How possible now we have galaxies, the sun, the Earth, Tokyo, Kyoto, temples, myself? How come? Well, myself, I'm not sure whether it's a good thing, but anyhow, I am here. This is the data. Okay, so, all right, so what is this, and why we have this light anyhow? So what we think now of the light is it's leftover the Big Bang, exactly like you would make a bomb explode, and you would feel the heat. That heat is actually radiation, something you don't see, but it's there, you feel it, right? And that's exactly that light over there. Right. Now, right, so on the other hand, as we said, we want to try to understand why that extremely beautiful, calm sea became galaxies. And one may say, hold on a second, we now know that the universe is actually expanding. By saying this, it means that, let me give you a short image of the expansion of the universe. Suppose we are sitting here on these tables, okay? Everybody is sitting here. We don't move. We are not moving. But after 5 minutes, we realized that each one of us became further away from each other, although we were not moving. So the only explanation we would say is the floor is expanding. So that your table becomes further from me and you get further from me. It's not we are moving, it's the expansion of the floor. Okay? Or it's another way to see it, it's like you're here at the North Pole and you say, oh, look, it's very cold. I want to go to a very nice tropical land. Let me go there. And the first thing you say, okay, let me see what's the distance. And you see the distance, well, it's about, 3,000 kilometers. Okay. After 5 minutes, let's say after 2 days, you prepared all the baggage, you say, okay, hold on a second, let me check once more what's the difference, what's the distance of this place from me. And you realize it's actually 3,500 kilometers. You say, hold on a second, what's going on here? And you wait another week, and it became 4,000 kilometers. So then we say the universe is expanding. Or you would say, in this case, in this example, you would say the Earth is expanding. But we are not moving on this Earth. It's just the radius of the Earth is expanding, actually. So that's something which is interesting. So then one may say, hold on, then maybe you have this very perfect sea of primordial light. Maybe by time, this thing becomes galaxies. But, I'm sorry. But the point is that it doesn't need to be. It could be very well that sea would expand by remaining the mirror perfect sea. Time is not enough. Right? What I mean is that if I have this microphone here, this microphone after 1 million years will probably be still the same mic, unless I break it or I do something. So that primordial light, the fact that the universe was homogeneous, might be still the same universe all over the time. And by the way, if that would have happened, we would not be here. So simplicity may not lead to anything interesting. Although from a physical point of view, it's something very easy to model. Oh, I have this perfectly equal universe everywhere, fantastic. fantastic, but we don't get anything interesting out of it. It's fantastic to, let's say, kind of control, but it's very, very boring. All right, so then the expansion, as I said, the universe was smaller in the past, and the fact that we had this primordial light, actually, it's another way to see that. This primordial light, by the way, we call it CMB, cosmic microwave background, because it's from the cosmos. It's a microwave. It's like exactly like when we heat up the pizza in the microwave, and it's a background because it's everywhere. But we saw the data show that, yes, it was very perfect, but there were really tiny ripples, really tiny sea waves, extremely tiny, but they were. So those ripples actually will be the part of the answer why we have now galaxies. But we had to a bit explain more what is this background radiation that I told you. This radiation, when we say radiation, the sun emits light and we feel heat from the sun. So we can attach a temperature to radiation. The temperature of this radiation is extremely low, 2 degrees above absolute zero. So it's minus 270 degrees. Right? So during the winter, that would not be the source that you would look like. You would search for, right, to get some heat. And the wavelength, as I said, is about microwave, so we call it millimeter centimeter scales. And there are 400 photons per cubic centimeters. Yes, in this very room, you take 1 centimeter square here, and you would see 400 photons, 400 waves of that light. But that's everywhere in the universe, okay? That's quite a lot. And now we have TV cable, so we don't see anymore, but still I was in a generation where there was cable, TV with antenna, and sometimes you had this kind of snow, TV snow we call it, right? So that radiation actually was a few percent of that TV snow. So all our grandparents were detecting that cosmic microwave background radiation, but none of them got a Nobel Prize. Right? That's a bit sad story, right? And you will say, So in other words, for those televisions, no matter how precise they would do technology, they would always find some few percent of snow they could not remove. All right, so that's, all right, so, and as I said, those ripples of energy, of temperature, is about 1 part in 100,000. So those sea waves are really, really tiny. Okay, so that's the picture there. So let me give you a very, very schematic picture. So we know for sure that the universe was that kind of light, and now we have these galaxies here. So something here in the middle happened, right? And we would like to know what really happened between here and here. Nowadays, we don't know exactly the whole history. And of course, we have still many things we don't understand, actually. That's part of the complexity of the system, right? On the other hand, if there would be everything understood, we would stop doing research, and we would probably go down into involution of mind, actually. All right, anyhow, so now we have to understand how to go from this, like, we call it actually soup of particles, like misoshiro, essentially, very, very homogeneous misoshiro, into galaxies, actually. So, and the point is that gravity is at work. So we have, this is something that's the non-trivial bit. It's not time, it's gravity, the thing that we get. All right, so we had how to get this galaxy, which are very complex object with many stars and so forth and so on, out of that initial soup. Well, gravity is the key concept. What it means is that once you have gravity, gravity tends to put things together, never puts things outside. Gravity is an attractive force, no matter what we do. Okay, that's the key. And the ripples are related to gravity. Let me show you why. So we know that large masses attract each other, right? Because, for example, the Earth is not going outside, flying away out of the sun. It's going around, but never leaves it. And another way, we remain on the surface of the Earth. No matter how, I cannot go to Olympic Games, but even those people who do very, very high jumps, they had to go back to Earth at some point. The point is that even small masses attract each other, so everything attracts each other. So then what happens is this. Now suppose that you have some ripples in this energy C. Those ripples means that you see a wave is something like this, means that you have a bit more of water here, a bit less water here. Being more water here means I have more mass here. So think this little bit more mass will attract more mass towards it. So the C wave, which was small, starts becoming bigger. Okay? That's the key concept of gravity. Yes. So, in other words, suppose about, once more, this is the ripple that I told you, the little C wave. And you know what happens is that, mass, okay, this is slightly different, but anyhow, so mass will tend to go into the more attractive region. So then, those then ripples, you remember that the initial picture that I had, you could see red and blue spot. The red spot means more mass. Therefore, in those red spots, you would expect by time to form more and more mass up to the level that you have a huge amount of mass and distinction between masses and vacuum. Anyhow, so the point is that I want to say this thing actually. Now, gravity is, by the way, this gravity thing is amazing because without gravity, we would not be here. But on the other hand, what happens that this beautiful C, which was perfectly simple, then the C waves becomes larger and larger, and you understand it becomes more complex and more complex. And you understand that to predict what's happening in a perfect flat C is very simple. Nothing will happen, right? Everything remains the same. But as long as you have, as soon as you have big waves, it's very hard to predict what's going to happen. Then complexity becomes difficult to analyze and also to understand what are its prediction. Then what people do, people put, these initial ripples in, and the gravity law, and they simulate, and they do some simulation with the computer. And actually, what people see is that this simulation at the end people start seeing that these masses start forming things that then they will become galaxies. Okay, so more or less, we have an intuitive understanding of how to produce galaxies. So that's okay already, actually. And as I said, the primordial light, so this is important also. So the primordial light actually is like this sea that I was talking to you. Is actually, you can, because it's light, it's more like a gas of particles, actually. In this gas, at small scales, sound wave will propagate. So these ripples actually are not static, but they move, like a sea in the wave, actually, like sea waves. So then gravity tends to compress this gas, and pressure resists, and that's why, so if I want to compress the sea, then the sea will act a, resistance, and this will create a wave which propagates, actually. Compressed photons become hotter, and that explains hot and cold spots in the sky. So that's what we are doing. We are trying to understand how structure forms in gravity models. So we have learned that gravity leads to the growth of structure. Growth of structure means the growth of structure, which then will become a galaxy. We know now how to interpret the non-smooth universe we see, and we have now a clear distinction between galaxies and intergalactic empty space. And simulations in computers tell us how our theory describes the dynamics for the growth of structure. So the idea is the following. Okay, so we have a computer, we put gravity, we put what we think is gravity, okay, gravity law, Newton, gravity, blah, blah, blah. And then simulation afterwards will give us a picture of the universe simulated. Then we take this picture and check against the real picture of the universe. Is it the same or not? If it's the same, okay, then gravity is what we think it is. If it's not, whoops, then gravity doesn't work in this way. That's exactly what I call here gravity reverse engineering. From the fact that we have data, we try to infer what gravity is by using our simulations. For example, suppose you have a very strong gravity, you would expect the galaxy to form very fast. If you have very weak gravity, galaxy would take longer to form. So that's exactly what I mean by reverse engineering. From the data, we want to see, we can map theories to this observable, which is how fast the growth of structure, how fast galaxies form. Right, so almost over with my talk, actually. But let me show you here, this is actual research. So far, I was giving more like kind of introduction to what we are doing, actually. Now, you see this is, this quantity here, so this is kind of time. It's like, see how this growth of structures, how fast the sea waves form. So this is how fast the sea wave form, how fast the galaxies form in terms of time. And you see, this is the standard model which people mostly use. But you see, the data have errors, okay? But you see, it's a bit too high. Even by eyes, you can see. It's okay, it's not going here. It's not too bad. But you see, it's a bit displaced high. So this means that the standard gravity, how we think gravity is, it's a bit too strong for the data. At least it looks like. So we propose a model which actually has a bit weaker gravity, and you see the fit is better, even by eyes, you see. So we are very interested here, and so the best fit is different from the standard one, actually. Now we are very excited. The point is that we cannot really see too much because these error bars are still too large. So we are waiting for new experiment to have more precise data, which will put very strict. Already some data here are not too bad. But in the future, they want to put half error bars. And then, of course, in that case, if there is really, if really gravity is weaker, we will see by eye, even more than now. So that's actually interesting. I mean, it's not only galaxies. So out of this complexity, we start seeing something that is not, cannot be explained by standard gravity laws. So we may have found actually those people in the experiment may have found some non-trivial behavior in complexity. Or maybe it's just experiments are not so very well done, and in the future they will just correct to standard things. So we are waiting for new experiment. By the way, so the fact that gravity may be weaker, but our model is just a model. We don't know whether our model is the good model to reproduce this non-standard behavior. Okay, so that's the conclusion. By the way, today we celebrate the birthday of Galileo Galilei. I was from my hometown, the same, actually, so I have to say something about today. Sorry about it. I am Italian myself, by the way, so I had to. And anyhow, so we have actually, today I tried to tell you that, the existence of primordial light is actually a very beautiful and simple universe. However, those little imperfections led to galaxy afterwards. That's beautiful, I would say. Right? I mean, and it's extremely difficult to do. Out of those tiny little things came out galaxies, suns, structures, the thing that we see at night. And then, so we obtain this complexity, which is difficult to understand, but, it's very compelling, but it's also very attractive, right? And so, using this growth structure, we actually want to see what really gravity is. That's now it seems to be still speculations, but it seems like gravity may not be so simple as we thought it would be. Thank you very much.